The next video in my series on weak interactions is how electron capture decay happens. Electron capture decay, abbreviated EC in most decay tables, is due to an electron being captured from an orbital electron around the nucleus into the nucleus, where it converts a proton to a neutron. And this is a form of beta decay. And it's a two-step process that involves quantum fluctuation interactions. You first have the neutron formation, and then you have a vacant orbital, which, by spontaneous emission, emits a photon. And both of those processes are mediated by separate quantum fluctuations. In the first step, we have the basic idea of the nucleus, the two orbitals I'll put here, and then the inner electron, typically it's a K-shell electron, is going to be absorbed by the nucleus, and then you have the photon. This changes the atomic number by 1, and so in one example that I'm very familiar with, iron 55 becomes manganese 55. It goes from 26 protons to 25 protons, but the total weight stays the same because you replace a proton with a neutron. So how the interaction happens, if you go back to my video on how a neutron forms, a proton, we know from scattering experiments, has a shell at its charge radius, and the shell appears to be composed of quantum fluctuations. So these quantum fluctuations have this protective shell, and it's rotating at the speed of light. And the electron also has a protective shell of polarized quantum fluctuations that are rotating at the speed of light. It comes from the quantum field, not necessarily to be thought of as part of the particle. In both cases, we can really think of the proton and electron being bare particles. So we have a case where quantum fluctuation is between the orbital electron and a proton within the nucleus. And the positron annihilates with the orbital electron, and then the electron, as normal, would become free. It normally would maintain the same state, but in this case, it's inside the proton, so it converts the proton to a neutron. Then once the proton converts to a neutron, we have an empty orbital that has to be filled. So an outer orbital shell, usually the L shell, will lose an electron. And this process is called spontaneous emission, because it's spontaneous emission of the photon, although it's not really spontaneous because it's mediated by a quantum fluctuation. So once again, we have an electron-positron pair. The positron annihilates with the outer shell electron, and then the electron deposits in the inner shell, the quantum electron. And then the annihilated electron-positron pair, because it has excess energy that doesn't go away, it turns into a photon with that specific energy. And if it's a L to K transition, that's called a K alpha energy X-ray that we can measure. And so this is typical of how the electron capture decay works. And as I said, it's a two-step process involving quantum fluctuations. There's no magic involved, there's no WZs involved, there's no neutrinos involved. It's quantum fluctuations that are responsible for all these interactions. And I'd also like to point out that the energy from the quantum fluctuation, from the first quantum fluctuation, becomes part of the neutron. It becomes part of the extra 782 keV of energy needed to get the mass of the neutron. So the mass difference between a proton and a neutron, or a proton plus an electron and a neutron, comes from the quantum field, comes from the quantum fluctuation. And this quantum tunneling is how it happens. And then in the second case, the energy of the quantum fluctuation ends up going back into the quantum field, and only the excess energy of the orbital shell energy is what's left. And that gets turned into a photon. So when we're dealing with the energy conservation principles, we have to consider interactions of energy moving in and out of the quantum field, particularly when we're dealing with neutron formation. So anyway, that's how electron capture decay happens. And I'll be doing more videos on other forms of beta decay in coming days, so look forward to them. And if you like the video, please like it, share it with your physicist friend, subscribe to see future and past videos. And if you'd like to read about these types of interactions, weak interactions, I have a couple papers I'll link to below. And I also have books that you can buy. And I'm retired and now an independent researcher, and if you buy one of my books, that helps me with my retirement, and I appreciate that. And I also have a Patreon account if you'd like to contribute to my costs of producing my videos. So thank you very much for watching.